Greetings, ladies and gentlemen. It is my pleasure to welcome you to this virtual tour of the laboratory facilities at the University of Toronto Institute for Aerospace Studies, or UTIAS. We will begin our tour at the Flight Simulation Laboratory. The centerpiece of this lab is the UTIAS Flight Simulator. The PI who conducts research in this lab is Professor Peter Grant. They are currently studying three main projects. The first is the identification of accurate post-stall flight models from pre-existing certification flight test data. The ultimate goal is improved post-stall models for training pilots to reduce accidents. Their second project involves the application of new robust state estimation techniques to helicopter model identification. The third project is with the National Research Council, and they are trying to measure the handling qualities of blended wing body models that result from computational fluid dynamic-based aerodynamic optimization. They're building a full 6 degree of freedom simulation model of optimized blended wing body models and would like to see if these models require full authority control to make them flyable, or if the more straightforward and easier to certify stability augmentation is sufficient. Professional test pilots will eventually evaluate the blended wing bodies in their virtual flight test environment. The Flight Systems and Control Lab is under the supervision of Professor Hugh Liu. They focus on the following research theme: to discover innovative flight control solutions for intelligent aerial systems, including unmanned aerial systems and autonomous aviation applications. They have a passion for working on creative ideas, yet sticking to a systematic approach of realizing these ideas by developing a dynamic model to describe the aerial system's behavior or aviation application phenomenon, and custom building integrated control to achieve desired missions, supported by experimental proof of concept flight demonstration. Their recent research projects include the following. First, coordinated drone delivery. They are working on flying a group of quadrotors in coordination to carry a payload of different shapes and sizes to significantly increase the payload delivery flexibility. Second, they are developing a novel vertical takeoff and landing aircraft and its control. It is an innovative tilt-rotor aquatic unmanned aerial vehicle, Aquafly, and is currently under design and development. The proposed configuration can land and take off from water surfaces and has a mechanism for automatic water sampling. Their third project is intelligent drone gaming. In this project, they are investigating the strategies of coordinating defenders to prevent an intruder or intruders from accessing a prescribed protection zone or target based on game theoretical approaches. Our next lab is the Flow Control and Experimental Turbulence Laboratory. Research is conducted in this lab under the auspices of Professor Philippe Lavoie. The centerpiece in this laboratory is a large wind tunnel with a working section of 0.8 meters by 1.2 meters and 5 meters in length. It has a top speed of 35 meters per second. It is specifically designed to have very low background turbulence intensity, below 0.05%, which facilitates stability studies. It has been used for fundamental fluid mechanics, aerodynamics, and turbulence research. Other tests have included seagull wings, a hybrid airship, high-performance triathlon bicycles, and UAV models. This smaller wind tunnel has a working section of 30.5 centimeters by 30.2 centimeters and is 2 meters long. It has a top speed of 40 meters per second. It is used primarily for experiments that can be done at smaller scales, proof of concept experiments, and undergraduate student projects. We now enter the Fusion Laboratory, which is under the supervision of Professor Jim Davis. One of the major challenges in the design and operation of a magnetic confinement fusion reactor is the close proximity of the hot fusion plasma and the solid surfaces which make up the confinement vessel. The core plasma will be at temperatures above 100 million degrees Celsius, while only a few centimeters away will be the internal armor, which will protect more sensitive structures like the superconducting magnetic coils. In some ways, the plasma materials interaction which occur in a fusion reactor are similar to the interactions of a reentry vehicle with the Earth's upper atmosphere. The history of the UTIAS fusion group goes back to such work done here during the 1950s and 1960s. The current focus of the fusion group is on the physics and chemistry of the interaction of plasma particles, mainly hydrogen isotopes, but other species as well, with various wall armor materials. To this end, they work with low-energy particle accelerators and other particle sources to simulate some of the particle surface interactions. The main facility is the dual beam accelerator, which is comprised of two independent particle accelerators, which allows them to simulate some of the complex bombardment conditions which might occur in a fusion reactor. Materials of interest include metals like tungsten and beryllium, as well as ceramics like graphite and silicon carbide. We now take a look at the Advanced Aerospace Structures Lab. The work performed here is done under the supervision of Professor Craig Steeves. Current areas of focus include topology optimization of hybrid microtrusses, morphing hybrid nanometal structures, tailored composite materials, and low thermal expansion lattices. Some recently completed doctoral research and master's research includes looking at compressive instabilities in metal-coated polymer microtrusses, the performance of nanocrystalline coatings under combined impact and fatigue loads, and bimaterial lattices with anisotropic thermal expansion. The next portion of our tour will take us through the UTIAS combustion laboratories. The tour guide for this portion will be Research Associate Taylor Ralt.
Hey, my name is Taylor. I'm a research associate here in the Combustion and Propulsion Lab at UTIAS. I'm going to give you a quick overview of what we do here for research. So one of the things we study is soot formation. And so we care about soot because it's produced in hydrocarbon flames. So if you're not aware, the bright orange glow from a candle flame, just like this, is actually produced by hot incandescent soot particles. So if I stick this little probe in here and let some soot build up on it, so you can see the black soot that's now on the probe. So the only reason it's orange in there is because it's so hot that it's incandescent, like the filament of a light bulb. And so what we're doing with this experiment here is we're looking at soot morphology. So our student Dominic, he has a laser here. He's going to shoot the laser light through a set of optics into the flame in a controlled fashion. And so then he'll detect the scattering from the light at different angles. And by detecting the intensity of the scattered radiation, we can gain information about the nature of the soot particles, like their size, their morphology, their fractal structure, which is basically how the little small subparticles are organized together to make a big soot aggregate. So that's our main project here, and we'll show you some other research that's related in our other labs. Alright, so moving on from our previous lab where we had atmospheric pressure laminar flames, in this lab we study laminar flames at elevated pressures. And so we care about soot formation at elevated pressures because practical engines actually operate at elevated pressures as well. The reason we do that is for improved thermal efficiency and improved power density. The unfortunate bit, though, is that soot formation actually increases with approximately pressure squared, and there's some fluctuation there. So we want to be able to study the different mechanisms of soot formation at elevated pressures. And so the way we do that is by studying similar little candle flames inside this pressure vessel, which can go up to 100 bar, and then we can use our optical diagnostics through these windows to be able to study our flames with different techniques such as soot spectral emission technique or using laser-induced incandescence, although that has some issues, and other optical techniques. So that's the primary reason we have this elevated pressure chamber, and so we can study flames at engine-relevant conditions. Alright, so one thing that is an issue inside jet engines is cooling. So inside an internal combustion engine, we have a dedicated cooling system, typically with water or ethylene glycol or some other coolant with its own dedicated system. But that's heavy, and so in an aviation gas turbine, we want to have our own dedicated cooling system, but with the fluid that's already on the plane. So we use jet fuel. The problem is, jet fuel breaks down at high temperatures, and so we need to be able to study how it breaks down and how it forms carbon deposits on the cooling tubes and even in the nozzles of our jet engine. So the way we do that is we have this feed system where we feed the fuel through this section of tubing. It's preheated a little bit, and then it is fed through this bath of hot water. And so there's a series of tubes through this hot water bath, which will have a controlled temperature. And so by controlling how long the jet fuel spends in this hot environment and the temperature of the water bath, we can effectively study how the jet fuel will decompose under certain conditions and how it will form carbon deposits. So this gives us insight into, of course, the way the fuel decomposes and how we can better design fuels or surface coatings or what have you inside our jet engines so we can mitigate these carbon deposits and the negative issues associated with that. Alright, so much like we were talking about in the other labs where we want to study flames and combustion phenomena under engine-relevant conditions, this is the ultimate way to do that. So all the other experiments are performed with relatively small laboratory-scale experiments where we can have more control over other parameters. But this allows us to bring all of that research together and actually study our flames under conditions that are actually relevant to gas turbine combustion. So in a jet engine, our flames operate at elevated temperatures, high flow rates, high pressures, and with a variety of different fuels. We have aviation gas turbines or land-based industrial gas turbines for power generation. So with this rig here, we can study experiments at these conditions. So we're able to study up to 25 bar, and we have air coming in at 450 degrees Celsius with maximum flow rates of up to about 1 kilogram per second at those conditions. So that's very similar to one small segment of an aviation gas turbine or of an industrial gas turbine of that nature. And so we can insert our various different rigs in through our end here, where we can insert our nozzles and whatever else we want to use to study our rig. So if we want to have a controlled, confined environment inside, we can place that in there with our nozzles, or we can have a more open flame. And then once we have that inside, we can study and investigate the reactions in the flames with optical diagnostics, again, through our optical access ports. So that's what these will be used for. The rig can also accommodate various fuels, so we have jet fuel, natural gas, hydrogen, and fuel oil, which are, of course, the relevant fuels for gas turbine and aviation gas turbine combustion. So, state-of-the-art facility, and once it's completed, we'll be able to perform research that can only be performed in a few locations around the world. Alright, so in the other labs, we have small laminar flame experiments where we can control a few parameters and investigate the results. But if we want to investigate more relevant flames for gas turbines, we actually want to produce model validation suited data such that we can actually have a flame that's similar to what goes on in a natural gas turbine. So that's what we have here. We have a model gas turbine combustor that's optically accessible with quartz windows, and we have a jet fuel spray surrounded by a swirling airflow. So we get a nice swirl stabilized spray flame, which is very much like what actually goes on inside of the aviation gas turbine. And so the reason we have the windows here is so we can use optical diagnostics to produce to get flow field data. So for this technique, we use particle image velocimetry, where we have a laser sheet that goes through the burner, and then we image particles that are in the flow with these cameras so we can resolve the flow field. We use other techniques, other laser diagnostics to image the amount of soot that's produced in the flame, and we also analyze our spray characteristics. So we can get our droplet size and things like that to characterize the flame and produce model validation suited data. So from this, we can then relay this to numerical modelers, and then they can generate models that can actually be used to design gas turbine engines.
We will now visit the Experimental Fluid Dynamics Laboratory, which is run under the auspices of Professor Elise Ekmekshi. The centerpiece of the lab is a large recirculating water channel. It continuously provides a uniform flow along its 5-meter-long test section. The walls of the test section are made of plexiglass material, which allows optical access to the flow. This facility can operate in free surface mode with no top covers, or as a closed tunnel using top covers. It is known that compared to a wind tunnel flow facility, water facilities have the advantage of slowing down the flow dynamics and thereby enable the capture and time-resolved analysis of highly unsteady flow behavior. This facility is therefore used to simulate the flow fields around scaled models of various bodies, including cylinders, landing gears, automobiles, Ahmed bodies, bridge models, micro-air vehicles, and others. The technical details of the facility can be summarized as follows. The width of the test section is 0.610 meters. The height is 0.762 meters in a free surface channel configuration and 0.686 meters in a closed tunnel configuration. The length of the test section is 5 meters. The speed range is 0.03 meters per second to 0.78 meters per second. We'll now visit the inside UTIAS robotics facility. The work done here is done under the auspices of Professor Angela Scholig and Professor Jonathan Kelly. Most of the space is a netted off area that can be used for inside testing of unmanned aerial vehicles. Professor Scholig is looking at many aspects of robotics in this facility. Some of these include deep neural networks for robotics, learning control theory and its foundations, with applications to safe and robust robot learning in unknown environments, and robotic swarms. There is a Vicon camera system in this space that allows the researchers to make accurate measurements of robot position. Professor Jonathan Kelly has a state-of-the-art mobile manipulation platform. It consists of a ClearPath Ridgeback mobile base, a Universal Robots UR10 manipulator with 6 degrees of freedom, a Robotique 3-fingered hand, a Robotique wrist force torque sensor. It is used for lots of interesting research, including imitation learning for manipulation, studies of singularity avoidance, multitask planning, and fastball catching. We will now pay a visit to the UTIAS Outdoor Robotics Laboratory. A central activity in this lab is self-driving car research. The blue car you see is named Zeus. This is the auto-drive competition car used by a student-run team of 100 students over the last 3 years. It has LiDAR and cameras. The team has won the competition 3 years in a row, and auto-drive is continuing for this year plus 4 more. The white car is Boreas, and it is a top-notch data collection platform that has 3 of the world's best sensors on it. An example project that it is being used for is to show that we can build a radar localization and mapping system that rivals LiDAR in nominal conditions and outperforms it in bad weather. The drone that you see here is being used by Professor Stephen Waslander for gimbaled camera visual odometry, autonomous target tracking, docking on moving vehicles, and precision navigation in the wind. This work is in collaboration with Ford and Drone Delivery Canada. The multicopter you see here is being used by Professors Tim Barfoot and Angela Scholig to work on visual navigation of UAVs. The large yellow off-road robot here, Grizzly, is used by Professor Barfoot as the main test platform for the visual teach and repeat navigation framework that he has been developing for over 10 years. We will now pay a visit to the UTIAS Mars Dome. This structure was originally constructed to test air cushion vehicles on a circular track. It is now used as a source of mock terrain for testing autonomous terrestrial vehicles. A mock aircraft crash site is also in the Mars Dome and is currently used to teach a course in aircraft accident investigation. Attached to the Mars Dome is the anechoic wind tunnel. This can be operated as an open jet, open return tunnel. The open jet is 0.6 meters by 0.6 meters with a top speed of roughly 75 meters per second. The facility has been used most recently for various airframe noise studies, including landing gear and a high-lift airfoil configuration. This concludes our virtual visit to the laboratory facilities at the University of Toronto Institute for Aerospace Studies. We hope you have found the tour informative and interesting.